Hello everyone. So in this chapter, we shall define a variable that would assign a number to every outcome of a statistical experiment. Now this variable is referred to as a random variable. So as an illustration, let us consider the experiment of tossing three coins. In tossing three coins, the number of outcomes is 2 times 2 times 2. So which gives us 8 possible outcomes. So you can actually make use of the tree diagram in order to list down all the possible outcomes when tossing three coins. So the outcomes are as follows. We have head, 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 tail, and so on and so forth until we have tail, tail, tail. Now let us define a random variable x, which represent the number of heads that occur in each outcome. So that means the outcome head, head, head will be assigned with x equals 3. The outcome head, head, tail is assigned with x equals 2. Same for head, tail, head, and tail, head, head. Now the outcome tail, tail, head is assigned with x equals 1. Same for tail, head, tail, and head, tail, tail. While the last outcome tail, tail, tail doesn't have a head. So therefore, it's assigned with x equals 0. So we can actually define a lot of random variables for this statistical experiment. So you can actually define a variable y that would represent the number of tails in each outcome. It could be a random variable z that would be defined as the number of heads minus the number of tails. So those are just examples of possible uh, variables that we can define to an experiment or that we can assign to each outcome of the statistical experiment. So in this slide, in this table, it is shown the assignment of values for each outcome of the experiment of tossing three coins. Okay, so you already saw these values in the previous slide earlier. So the only possible values for x in that experiment are 0, 1, 2, and 3. Now, since we only have three coins, then the maximum number of heads that will occur in each outcome is 3. And the lowest possible number of heads is 0 because if we toss three coins, it's possible that there would be no head. So the only possible values for x are 0, 1, 2, and 3. So the variable x defined in that experiment, or the number of heads in tossing three coins, is viewed as a random variable. So what is a random variable? Now, a random variable is formally defined as a function that assigns or associates a real number with each element in the sample space. Now let's try to consider another experiment. Okay, so an experiment consists of rolling a pair of dice. So let us give some possible outcomes of this experiment. So remember, when we roll a pair of dice, there are 6 times 6 possible outcomes or 36 possible outcomes. So let us list down some of these 36 possible outcomes. Okay, it could be that the outcome is 6 comma 2, or it could be 3 comma 2, or it could be 1 comma 3, it could be 5 comma 4, it could be 6 comma 6. So these are just 5 possible outcomes out of the total of 36 outcomes of the experiment. Okay, so now what is the random variable defined? So the random variable defined here is x, which represents the sum on the top faces of the pair of dice. Okay, so what are the values assigned to each outcome listed in the first bullet? So in the first outcome, 6 comma 2, the sum on the top faces of the pair of dice is 8. So we can assign this with x equals 8. For 3 comma 2, this is assigned with x equals 5. For 1 comma 3, this is assigned with x equals 4. For 5 comma 4, this is assigned with x equals 9. While for 6 comma 6, it's assigned with x equals 12. So these are the possible or some of the possible values of x of the random variable. Okay, so now in this particular experiment, the lowest possible total or sum is 2, and the highest possible total or sum is 12. So that means the random variable will run from 2 up to 12. So these are the only possible outcomes of or the only possible values of the random variable x. So it cannot be x equals 1, it cannot be x equals 0, or it cannot be x equals 13. So it should only be from 2 up to 12. So let's have another scenario. Let us consider an experiment consisting of selecting 5 cards from a standard deck of cards. So let x be a random variable representing the number of queens in the selection. So the first question is, how many outcomes are there in the experiment? So since the experiment is selecting 5 cards from a standard deck of 52 playing cards, then the total number of outcomes would be 52 combination 5. You can just use your calculators to determine the exact value of this quantity. Okay? And then the second question is, what are the possible values of x? So recall that x here is defined as the number of queens in the selection. So let's say we select 5 cards. How many queen cards are there in the selection? So the possible values of x would be, x could be 0. So x equals 0 means that there are no queens in the selection, or there are no queens selected. It could be that x is equal to 1, which means that there's exactly 1 queen card in the selected 5 cards. Or it could be x equals 2, x equals 3, up to x equals 4. So x equals 4 means that that all of the queen cards are part of the selection of 5 cards. Now, the random variable x cannot be equal to 5 because there are only 4 queens in the standard deck of cards. Okay, now for the third question, for each possible value of x, let's list down one outcome of the experiment. So for x equals 0, we can list down any set of 5 cards that doesn't contain a queen. So for example, if we have, let's say, King of Hearts, King of Diamonds, King of Spades, Jack of Hearts, Jack of Diamonds. So this set of 5 cards doesn't have a queen in the selection. Now for x equals 1, there should be exactly 1 queen in the selection. So which means it could be any queen card, and then the rest of the 4 cards would be non-queen cards. So for example, it could be 5, 7, ace, and 2. Now for x equals 2, there should be exactly 2 queen cards, and then the rest would be other cards. So it could be king, jack, 10. And then x equals 3, there should be exactly 3 queen cards, and then the other 2 cards will be other cards. And then for x equals 4, that means all the queen cards are selected. And then there's an additional card which is not a queen card. So it could be, let's say, jack. Okay? Now, since a random variable is considered a number, or is a number assigned to each outcome of an experiment, then it's considered a quantitative variable. So just like quantitative variables, it has two types. It could be discrete random variable or a continuous random variable. So a discrete random variable is a number assigned to an outcome of the sample space wherein the number results from counting. The examples or the random variables in example 6.1 and 6.2 are discrete random variable. So recall that in example 6.1, the random variable is the sum of the top or the top faces of the pair of dice. So those numbers 2, 3 up to 12 are numbers resulting from counting. So therefore, it's a discrete random variable. Now for example 6.2, the random variable defined is the number of queens. And number of queens is an example of a discrete quantitative variable. So therefore, it's a discrete random variable. Other examples of discrete random variables are as follows. So suppose that there are 15 statistics sections, and we let x to be the number of students who are absent in those 15 sections. So for example, section 1 has 2 absences. Section 2 has 4 absences. Section 3 has 0 absences. Section 4 has 9 absences, and so on and so forth. So in this case, x could be from 0, 1, 2, and so on. Now, for the second example, we have x represents the number of wrong answers in a 10-item multiple choice test of 50 students. So for example, student 1 committed 1 mistake. Student 2 committed 0 mistakes. Student 3, let's say, committed 5 mistakes, and so on and so forth. So in this case, x could be from 0, 1, up to 10 because there are only 10 items in the multiple choice test. Now, for the third example, x represents the number of missed shots before a successful shot in a basketball game of 20 players. So, for example, the first player could miss 5 shots before making his first successful shot. Second player could have 7 missed shots before making the first successful shot. Or player 3 could have made his first successful shot on his first attempt. So that could be x equals, or that would be x equals 0. So in this case, x could be 0, meaning the player made his first successful shot on his first attempt. X equals 1 means that the player has missed one shot before making his first successful shot. X equals 2 means that the player has missed 2 shots before making his first successful shot. And then this will go on until infinity. Now, if a random variable would include numbers that result from measuring, then that means the random variable is continuous. Examples of continuous random variables are, let's say, the amount of time in minutes it took 50 students to complete a test. Remember, time is being measured, so that's why amount of time is considered a continuous random variable. So same as for weight and age, because these variables are being measured. Now next, no, a random variable has an associated probability mass function or probability distribution. So this probability distribution shows the probabilities that the values of the random variable x will happen. So the probability mass function is symbolized by small p of x. So this is the probability mass function, or sometimes we refer to it as PMF of a discrete random variable x. So it's just a listing of all possible values of the random variable x and their corresponding probabilities. So that's why we have here small p of x as the probability that the random variable x is equal to a specific value of x. So let's say if x is equal to x sub 1, that means the probability or small p of x sub 1 is equal to the probability that the random variable x is equal to x sub 1. Now, if let's say the value of x is not among the values x sub 1 up to x sub k, then its probability must be 0. So for example, if we have the following table, let's say x equals 0, x equals 1, and x equals 2, and then the associated probabilities are let's say 1/4, 2/4, and 1/4, then this means that small p of 0 is equal to the probability that the random variable x is equal to 0, which is equal to 1/4. Now, small p of 1 is equal to the probability that the random variable x is equal to 1. And from the table, it says it's equal to 2/4. And small p of 2 is equal to the probability that the random variable x is equal to 2. And from the table, it's equal to 1/4. So for the properties of the probability mass function, the probabilities are always non-negative. So actually, this is just the property of probability that it's from 0 up to 1. And then second, if you get the sum of the probabilities of the probability mass function, the total will always be equal to 1. That's an important property of the probability mass function. So let us consider again the experiment in situation number 1. So in situation number 1, the experiment is tossing of 3 coins, and the random variable x is defined as the number of heads. So if we're going to toss 3 coins, the possible values of x would be 0, 1, 2, and 3. So x equals 0 means that there are no heads in the outcome. X equals 1, there's exactly 1 head in the outcome. X equals 2 means that there are exactly 2 heads in the outcome. And x equals 3 means that there are exactly 3 heads in the outcome. Now in the second row, you find the probabilities associated to the values of x. So remember, if x is the number of heads and the outcome is tail, 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 that means x is equal to 0. And the probability that the outcome doesn't have a head is 1 out of 8. For x equals 1, the outcomes would be tail, tail, head, tail, and head, tail, tail. So the probability is 3 out of 8. For x equals 2, the outcomes are head, head, tail, tail, head, and tail, head, head. So the probability is 3/8. While for x equals 3, the only outcome is head, 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 and the probability is 1/8. Now observe that all these probabilities here, the 1/8, 3/8, 3/8, and 1/8, they are all non-negative. So it satisfies the first property of the probability mass function. Now also, if we're going to add all these probabilities, the sum is 8/8, which is equal to 1. So this also satisfies the second property of the probability mass function. For another example, let us construct the probability distribution of the random variable x in example 6.1. So in example 6.1, recall that the random variable x is the sum on the top faces in a pair of dice. So the lowest possible sum is 2 and the highest possible sum is 12. Now, the only outcome that would correspond to a sum of 2 is the outcome 1, comma 1. So the probability that x equals 2 or the sum is equal to 2 is 1/36. Now, for x equals 3, the only outcomes are 1, comma 2 and 2, comma 1. So the probability is 2 out of 36. Now, for x equals 12, the only outcome is 6, comma 6. So the probability is 1/36. So you can just verify that these are the probabilities when x is equal to 4 up to 11. Now observe that all the probabilities are non-negative, and when you add all these probabilities, the total is always equal to 1. Now for the second illustration, construct the probability distribution of the random variable x in example 6.2. Now recall that in example 6.2, the random variable x represents the number of queens in the 5-card selection. So since we are selecting 5 cards from 52 playing cards, the total outcomes of the sample space would be 52 combination 5. And then, since the random variable x is the number of queens, the possible values of x would be 0, 1, 2, 3, and 4. So x equals 0 means that the selection does not have any queen cards. X equals 1, 2, 3, 4 means that the selection has exactly 1, exactly 2, exactly 3, or exactly 4 queen cards respectively. Now the probabilities is that whenever the selection doesn't have a queen card, that means the total number of ways of selecting 5 cards with no queen cards would be 4 combination 0 times 48 combination 5, because that means all the 5 cards selected will come from the 48 non-queen cards. Now for x equals 1, there's one queen card selected from the 4 queen cards, and we multiply it with the total number of ways of selecting 4 cards from the 48 non-queen cards. And then same idea or the same concept will be applied whenever we have x equals 2, x equals 3, and x equals 4. So you can just review your counting techniques and probability lessons in order to identify these probabilities. Okay, another example, Mark, a quality control engineer of a large computer firm, inspects a large shipment of printed circuit boards or PCB. The shipment of 1,000 PCBs were inspected for defects. Mark found that 750 of the PCBs have no defects, 100 with one defect each, 75 have two defects each, 50 have three defects each, and the rest have five defects each. Let us give the probability distribution function. So the experiment here is to select a printed circuit board. So the sample space would be the 1,000 printed circuit boards. And then what we're counting is that x is the random variable that would represent the number of defects. So according from this problem, the possible values of x are x equals 0 or no defects, x equals 1 meaning there's exactly one defect, and then we have x equals 2, x equals 3, and x equals 5. Now the probability that the printed circuit board doesn't have any defects would be 750 over 1,000. Exactly one defect means that the probability is 100 over 1,000. X equals 2 means that there are 75 over 100 chance that there will be exactly two defects. For exactly three defects, the probability is 50 over 1,000. And then for x equals 5, the probability is 25 over 1,000. So this is the probability mass function or probability distribution function for this problem. And finally, the probability mass function of a discrete random variable is given by the formula small p of x equals small c times 1/4 raised to x minus 1 whenever x is equal to 1, 2, 3, and 4. And the probability is 0 if whenever x is not among these values. Okay, so the question is, find the appropriate value of the constant c for p of x to qualify as a probability mass function. So in this case, now we shall create the table first. So we have the random variable x and the possible values of x. And then the probabilities are in the second row. So to get these probabilities, we need to substitute each value of x into the formula above in order to get the probability. So if x is equal to 1, that means the probability is c. If x equals 2, the probability is 1/4 times C. If x is equal to 3, the probability is 1 over 16 times C. And whenever x is equal to 4, the probability is 1 over 64 C. So since we want that this probability, that this table, since we want that this table should satisfy the probability mass function properties, then the total of these probabilities must sum up to 1. So solving for C, we multiply both sides by 64, and in the left side, we distribute the 64 to all of the terms. So we get 64 times C plus 16C plus 4C plus C equals 1 times 64 is 64. And then adding the terms in the left side, we get 85C and equate it to 64. And then dividing both sides by 85 will give us C is equal to 64 over 85. So if the value of C is 64 over 85, then this particular probability mass function or this table will qualify as a probability mass function. So this ends our video for the random variables, and in the next video, we shall define what is the average and what is the variance of a random variable x.